everyone, my name is Monica. We're happy to have you with us for getting started with the basics of IP. In this series of videos, we will be moving step by step to help you gain a systematic understanding of all aspects of the field of data communications, including data networks, switching, security, routing, reliability, BGP, and multicast. Now let's get started.
After you finish this training session, you will understand basic spanning tree concepts, the process of computing spanning trees, basic spanning tree protocol configuration, STP improvements in the multiple spanning tree protocol, and basic MSTP configuration. The figure shows a simple network. It consists of two Layer 2 switches, a PC, and a server. If a single point of failure occurs, the whole network is disconnected. Such a network is not robust and lacks redundancy. To enhance network redundancy, the following network architecture is selected. This network architecture, however, introduces loops. To prevent loops, a time-to-live field is added to the IP packet header of a Layer 3 data packet. The TTL decreases by 1 each time the packet passes through a router. If the TTL decreases to 0 on a router, the router discards the data packet and replies with an ICMP TTL timeout message to the source. The TTL helps prevent the packet from being looped. The loop shown in the figure consists of 3 switches. This is a typical Layer 2 loop. Data frames are transmitted within the Layer 2 loop, and Layer 2 switches transparently transmit them. In this situation, using a TTL field cannot prevent a loop. Loops can result in a variety of problems, such as broadcast storms. When a switch receives a data frame, the switch performs the following: obtains the source and destination MAC addresses in the frame header, learns the source MAC address, adds the source MAC address into the MAC address table, generates a mapping between the MAC address and the port that receives the frame, searches in the MAC address table for a port matching the destination MAC address and forwards the frame through a matching port. If no match is found, the switch floods the frame to all ports on the network, except for the port that receives the data frame. SW3 receives a data frame sent by the PC. If SW3 finds no entry matching the MAC address or receives a broadcast frame with an all F's destination MAC address, SW3 replicates the data frame and broadcasts the frame through all the other ports. Upon receipt of the data frame, SW1 and SW2 flood it too, resulting in a broadcast storm. A broadcast storm continuously consumes resources on the 3 switches, causing CPU usage to soar to over 90%. Loops also cause errors in the MAC address table. After SW3 receives a unicast data frame, it finds no entry matching the destination MAC address and floods the data frame. Upon receipt of the data frame, SW1 creates an entry mapping the source MAC address to the local port connected to SW3. Upon receipt of the data frame broadcast by SW3, SW2 transmits the data frame to SW1. SW1 creates another entry mapping the source MAC address to the local port connected to SW2. The mapping between the source MAC address and SW1's port keeps changing, which is called MAC address flapping. There are many causes for network loops. One example is when network redundancy is manually provided to enhance network robustness, a loop may occur. A configuration mistake may also result in a loop. Therefore, it can be a challenge for a network to ensure redundancy and prevent loops. The STP protocol helps address this problem. First, let's look at STP principles. The three switches on the network run STP and exchange STP packets. STP packets are called Bridge Protocol Data Units. After receiving a BPDU, a switch runs STP to compute a path. If a loop occurs, STP blocks a port to break the loop. If a link fails on another port, the previous port is unblocked. STP helps the network implement redundancy and prevent loops. For instance, in the preceding figure, if a link between SW1 and SW3 fails, SW3's port connected to SW2 changes from blocked to unblocked, which implements link redundancy. Next, we will discuss STP operations. STP can block a specific port or multiple ports. STP follows 3 steps to determine whether to block a port. STP selects a root bridge, which is a root switch for an entire switching network. Follow-up computation is performed based on this root bridge. STP selects a root port on each non-root bridge. The root port is connected to the root bridge. STP selects a designated port on each segment. STP blocks a port that is not a root or designated port. STP uses several parameters to complete computation. The parameters are included in BPDUs. Switches exchange BPDUs to run STP. In the initial state, each switch considers itself as a root bridge by default and floods the BPDU across a network. Upon receipt of BPDUs sent by the other switches, a switch selects a root bridge. Then the root bridge floods BPDUs and the other switches relay BPDUs sent by the root bridge. A BPDU is an STP protocol packet and contains multiple fields. The 4 important fields are the root ID, root path cost, bridge ID, and port ID. The root ID is the ID of a root bridge. The path cost indicates the cost of a path to a root bridge. The bridge ID is the ID of a network bridge that relays BPDUs. A bridge ID identifies an STP switch. The port ID identifies the port that sends or relays BPDUs on a switch. STP compares the root ID, path cost, bridge ID, and port ID parameters in sequence when computing a spanning tree. A smaller value indicates a higher priority. Each STP switch is assigned a unique bridge ID. The bridge ID is 8 bytes long and consists of 2 subfields. One subfield is a 2-byte priority. The priority value default is 32,768. A bridge ID priority must be a multiple of 4096. A smaller value indicates a higher priority. The other subfield is a 6-byte MAC address. The MAC address in the bridge ID is the backplane's MAC address on a switch. STP compares bridge ID priorities to select a root bridge. The switch with a smaller priority value is selected as the root bridge. If the priority values are the same, the MAC addresses in the bridge IDs are compared, and the switch with a smaller MAC address is selected as the root bridge. The path cost represents the distance from a switch port to a root bridge. Each STP-capable switch's port maintains a path cost that is inversely proportional to the port bandwidth. The path cost is computed in accordance with 802.1t by default. The following table describes the mapping between port bandwidth values and path costs. SW1 is the root switch and periodically floods BPDUs over the network. SW2 uses GE000 to receive the BPDUs and another port to forward the BPDUs. The process is called relay. The route ID in a BPDU is SW1's bridge ID, and the bridge ID is SW2's bridge ID. The process on SW3 is similar to that on SW2. The bridge ID is changed to SW3's bridge ID. The BPDU sent by the route bridge carries the path cost of 0. When the BPDU passes through SW2, the path cost is added to the port cost of the port receiving the BPDU on SW2. The port cost is $20,000. After the BPDU is sent by SW2, the path cost is unchanged. When the BPDU reaches SW3, the path cost becomes $20,000 plus $200,000 because the port receiving the BPDU provides megabit bandwidth on SW3. Each switch port running the STP protocol is assigned a unique port ID. The port ID is 2 bytes long and also has 2 subfields. One subfield is a 1-byte port priority. The priority value is an integer ranging from 0 to 255, and the default priority is 128. A smaller value indicates a higher priority. The other subfield is a 1-byte port number. A smaller port number is preferentially selected. If GE000 and GE001 have the same priority, GE000 is selected. Step 1. The switch with the smallest bridge ID priority value is selected as the route bridge in each broadcast domain. Switches compare MAC addresses if the bridge ID priorities are the same. In this example, the 3 switches all use the default priority. SW1 has the smallest MAC address and is selected as a route bridge. Step 2. The other 2 non-route bridge switches select route ports. SW3 has port 1 and port 2, both of which receive BPDUs. SW3 compares the route IDs, path costs, bridge IDs, and port IDs to select a route port. The route ID of both port 1 and port 2 are SW1's bridge ID. The route IDs are the same, and then the path costs are compared. SW3's port 1 receives BPDUs sent directly by SW1, and the path cost is 0 plus port 1's port cost. SW3's port 2 receives BPDUs forwarded by SW2's port 1. The path cost of SW3's port 2 is the sum of the port costs of SW2's port 1 and SW3's port 2. The port cost of SW3's port 1 is equal to that of SW3's port 2. SW3's port 1 has the smaller path cost. Therefore, port 1 is selected as the route port. SW2's port 1 is selected as the route port in the same way. Step 3. A designated port is selected on each segment. The link between 2 switches is a segment. All ports of the route bridge are designated ports. In other words, designated ports of the segment connected to the route bridge must be route bridge's ports. In the figure, SW2 and SW3 compare 2 ports between the segment. The 2 ports have the same route ID. The path costs are compared. The path cost of BPDUs received by SW2's port 2 is the sum of the port costs of SW3's port 1 and port 2. The path cost of BPDUs received by SW3's port 2 is the sum of the port costs of SW2's port 1 and SW3's port 2. Based on link bandwidths, SW3's port 2 has a smaller path cost. Therefore, SW2's port 2 is selected as a designated port. Step 4. SW3's port 2 is not a route port or a designated port. It is a non-designated port and is blocked to break the loop on the network. If a link between SW1 and SW2 fails, STP unblocks SW3's port 2. A switch port running the STP protocol has 5 stages. A port in the disable state does not forward BPDUs or data traffic. A port in the blocking state only receives and processes BPDUs but does not forward user traffic or learn MAC addresses. A port in this state has a maximum age time and its default value is 20S. If the port does not receive a BPDU within 20S, the port switches to the listening state. A port in the listening state does not receive or forward user traffic or learn MAC address. The port undergoes role selection to determine whether the port is a root port or designated port, or whether it is to be blocked. If the port is selected as a designated port, it enters the learning state. A port cannot change directly from the listening state to the forwarding state. This is because the port in the listening state and its MAC address table entry are empty. If the port changes directly to the forwarding state, the switch would simultaneously receive and flood a great amount of traffic. To prevent such flooding, the learning state was introduced. After a port in the listening state is selected as a designated port, it enters the learning state 15S later. When a port enters the learning state, it waits 15S, learns source MAC addresses in data frames, and maintains its own MAC address table. The port then enters the forwarding state. A port in forwarding state receives and forwards user data frames, receives and forwards BPDUs, and learns MAC addresses. In conclusion, a switch port takes 30S to 50S to transition from the blocking state to the forwarding state, which is relatively slow. To speed up state transition, a port can be defined as an edge port, which can swiftly switch from the blocking state to the forwarding state without the delay of 30S to 50S. STP detects network topology changes by receiving network topology change notification BPDUs. If a physical link between switches A and B fails, Switch B detects the topology change and sends a TCN BPDU. Upon receipt of the TCN BPDU, each switch replies with an ACK BPDU and forwards the TCN BPDU to the root bridge. After the root bridge receives the TCN BPDU, the root bridge also replies with an ACK BPDU. The root bridge sets the TC flag to 1 within 35S and floods the TCN BPDU to notify the other switches of the network topology change. Upon receipt of the TCN BPDU with the TC set to 1, the other switches reduce the lifetime of the MAC address table to 15S to speed up the MAC table update. Once the topology of the switching network changes, some entries in the MAC address table become unavailable. The STP topology takes a long time to detect the change and respond. Some sensitive services do not allow for significant periods of network interruption. To reduce network interruption, MSTP is used. This slide describes basic STP configurations. The default spanning tree type of a switch is MSTP, and the default priority is 32,768. Check whether the STP protocol needs to be activated on the 3 networks. STP does not need to be activated in Figures 1 and 2. In Figure 3, all devices are switches and several Layer 2 loops appear. In this case, STP must be enabled. A network with only switches must not contain a loop. In Figure 1, 4 switches belong to VLAN 10, and 2 trunk links allow VLAN 10 data to pass. In this situation, a loop occurs. In Figure 2, 2 switches belong to VLAN 10 and are connected to the trunk interface belonging to VLAN 10. The 2 switches below belong to VLAN 20 and are connected to the trunk interface added to VLAN 20. Data frames can be forwarded and are looped. In Figure 3, ports are added to VLANs. SW1's port A and SW2's port B are added to VLAN 30. SW1's port B and SW3's port A are added to VLAN 10. SW3's port B and SW4's port A are added to VLAN 40. SW4's port B and SW2's port A are added to VLAN 20. This network contains no loops because SW3's port A belongs to VLAN 10, and SW3's and SW4's trunk ports allow VLAN 40 data to pass, but not VLAN 10 data. This slide describes drawbacks to STP and their solution. In this example, a network contains a great number of VLANs, which share a spanning tree, and one port of SW3 is blocked. The link between SW3 and SW2 becomes unavailable, which reduces network resource usage. To improve network resource usage, each VLAN is mapped to a specific spanning tree, which is called per VLAN STP, to implement Layer 2 traffic load balancing. This method also has a drawback. If a network has many VLANs, each switch computes 20 spanning trees. If the network topology changes, all switches recompute to the 20 spanning trees, which consumes a lot of switch resources. MSTP bundles VLANs into 2 groups. VLANs in one group are mapped to instance 1, and VLANs in the other group are mapped to instance 2. A spanning tree is generated for each instance. Therefore, in this instance, there are just 2 spanning trees. When instance 1 is running, a port on SW3 is blocked. When instance 2 is running, another of SW3's ports is blocked. MSTP is compatible with STP and RSTP and uses multiple instances to isolate service and user traffic. This slide describes MSTP configuration. On the 3 switches, VLAN 10 and VLAN 20 are mapped to instance 1, and VLAN 30 and VLAN 40 are mapped to instance 2. In instance 1, SW1 is configured as the primary root bridge, SW2 is configured as the secondary root bridge, and SW3's GE0023 is blocked. In instance 2, SW2 is configured as the primary root bridge, SW1 is configured as the secondary root bridge, and SW3's GE0022 is blocked. This slide describes how to configure MSTP on SW1. After the basic configuration is complete, SW1 becomes the primary root bridge and SW2 becomes the secondary root bridge in instance 1. The basic configuration of SW2 is similar to that of SW1. The difference is that SW2 is the primary root bridge and SW1 is the secondary root bridge in instance 2. The basic configuration of SW3 is similar to the basic configuration of SW2 and SW1. The difference is that no priority of a spanning tree instance is set on SW3. The default priority of 32,768 is used. This slide describes the basic configuration of SW3's ports. After the configuration is successful, data of VLAN 10 and VLAN 20 is transmitted only through the link between SW1 and SW3. Data of VLAN 30 and VLAN 40 is transmitted only through a data link between SW3 and SW2.